Hello, Physical Science. This is Mr. B, and we are going to kick off Section 3 today. And there's several different things we're going to take a look at in Section 3. It's going to focus on mechanical advantage and efficiency. So we're going to take a look at if a machine actually benefits us at all. So we can actually put a number to how much it is actually helping us out with increasing the input force into a greater output force and things like that. So it'll make more sense if we just jump right into it. So for our example, they give is a nutcracker, and it is a machine, which we learned about, that converts the input force applied to it into a larger force that is actually capable of cracking a nut. So we're not able to just take a pecan or something like that and just smash it in our hands. We need a tool like this. We can apply the same amount of force to the input, and they will increase that, and it will give us enough force to actually crack the nut. And because it increases the force, the nutcracker has a mechanical advantage greater than 1. So mechanical advantage is going to be the first thing we're going to focus on, and we're going to have two types. So one of our big key questions is actually comparing the two types. We have actual mechanical advantage versus ideal mechanical advantage, but we'll get to that in a second. But just in general, our definition for mechanical advantage, it's if of the mechanical advantage of a machine is the number of times that machine increases in input force. So how much the machine can actually multiply the force that we put into it. And again, we can measure that in two different ways: the actual mechanical advantage and then the ideal mechanical advantage. And because friction is always present, the actual mechanical advantage of a machine is always going to be less than the ideal mechanical advantage. So that will make more sense because ideal mechanical advantage is calculated in a frictionless environment. So therefore, because we have to account for friction, our actual mechanical advantage is always going to be less. So those are just some of the big ideas, and they're now going to make more sense once we break them down a little bit further. So our first type of mechanical advantage is actual, and it's going to be abbreviated AMA. So if anytime you see that, that stands for actual mechanical advantage. And the mechanical advantage determined by measuring the actual forces acting on a machine is the AMA, or actual mechanical advantage. And we can calculate this out by taking the ratio of output force to input force. So it's pretty simple. I think our next slide actually has that. Okay, so yeah, you just divide the output force, so how much force is generated, over how much force you put in, and that will give you the actual mechanical advantage of the machine. It's pretty simple. What is it putting out over what you put into it? And then the example they give is a loading ramp, and the mechanical advantage of a ramp with a rough surface is going to be less than that of a similar smooth ramp because a greater force is needed to overcome friction. So you're going to have to put more into it, but you're getting the same amount out of it if you have a rough force or if you have a rough ramp. So that's going to lower your mechanical advantage because you're going to have a greater input force to overcome the friction. So we will do some calculations with this in class. So I don't think they give us any sample problems with that. I think they move on to our next one, which is the ideal mechanical advantage. So this is our IMA. So our first one, actual mechanical advantage. The ideal mechanical advantage, I would definitely write this down too, is the mechanical advantage in the absence of friction. So this is in a perfect world. If there was no friction acting, what would the mechanical advantage of this machine be? And because friction is such a prevalent force here, and it reduces mechanical advantage, engineers often design machines that use low friction materials and lubricants. So it's always a constant battle with engineers trying to overcome friction and to really get to as close to this ideal mechanical advantage as they possibly can. And we can actually calculate ideal mechanical advantage. So when we calculate what it is in a perfect world, we don't actually measure the force, we measure the distances that are involved because the distances don't change. So what can we do to get this from point A to point B with as little or with this as much ease as possible? So what is our ideal mechanical advantage going to be? Again, we're not going to worry about the force because the force always has to deal with friction. We're just dealing with distances. What do we got to do to get from point A to point B? So we take the distance that we actually move it, that's our input distance. So if I push something 5 meters, that would be the input distance, and then the output distance is how far it actually moves. And that doesn't make a lot of sense how I just said it, but we will do an example problem, and that we'll hear in a little bit, and that will make this one make more sense. So The cable supporting the gondola, which is this little box right here, it forms an inclined plane, which is a type of machine, and then the inclined plane is used to move people up to the top of the mountain. So how is this going to apply to our ideal mechanical advantage? We will see, again, the gondola uses the inclined plane formed by its supporting cable to more easily move people uphill. So the increased horizontal distance, the input distance, is greater than the vertical gain in height. So this little cable right here is going to be longer than actually how high that we move, the output distance. So the inclined cable gives the gondola a mechanical advantage that is greater than 1. And again, that might not make as much sense, but I think the sample problems for the ideal mechanical advantage make a little more sense. So our example here for calculating ideal mechanical advantage is a woman drives her car up onto wheel ramps to perform some repairs. So if she drives a distance of 1.8 meters along the ramp to raise the car 0.3 meters, what is the ideal mechanical advantage of the wheel ramps? So she drives her car a distance of 1.8 meters, and then as she's driving that 1.8 meters, her car raises 0.3 off the ground. So we are going to use that information to calculate our IMA. So we're going to read what information we're given, the input distance, so what distance are we responsible for? So we moved it 1.8 meters, and as a result, the ramps increase it by 0.3 meters. So we didn't do the output distance. The output distance is what the machine helps us move. So those are the two things we are given. Oh, and now, which unknown are we going to try to calculate? We're looking for ideal mechanical advantage because that's what it says right there in the problem. And now we are just going to figure out our formula. The ideal mechanical advantage is input distance over output distance, and then we just replace each variable with its known. So 1.8 over 0.3 equals 6. And for now, if you notice here, the meters cancel out, so we have no label for mechanical advantage. So that's probably good news for some of you, because you guys don't like to remember the labels for everything sometimes. So when we talk about mechanical advantage, there is no label because we took meters over meters. The meters cancel each other out, and so we just have a number, which is 6. And is our answer reasonable? It says yes. Because our input distance is greater than the output distance, and then it seems reasonable. So now, again, for extra credit on the top left corner, here's our first problem you can solve. And I'm not going to take the time to read it, so that's one's for extra credit. Oh, almost gave you the answer there briefly. If you're, maybe I won't count that one since I might have just given you the answer. Here's our second one you can do for extra credit. And then the third one you can do for extra credit. And we will do sample problems in class, but these are just another way for you guys to earn a couple extra credit points here before the end of the quarter. And so to wrap this up, so that when that's ideal, we've had actual mechanical advantage, ideal mechanical advantage. Now we're going to deal with efficiency. So efficiency of a machine, one of the big key ideas is that it is always going to be less than 100%. So the percentage of work input that becomes work output is the efficiency of a machine. So that's our actual definition. So I definitely make sure you have that written down. And because there is always some friction, the efficiency of any machine is always less than 100%. So we learned you can't get more work out of a machine than what you put into it. So your machine can never be 100% efficient, kind of for the same reason, because the friction is always present. So efficiency is the percentage of work input that becomes work output. And our efficiency is usually expressed as a percentage, so we just take our work output over our work input, we multiply it by 100. It's pretty simple. And the example they're going to give is if the efficiency of a machine is 75%, then you know that 75% of the work input becomes work output. So that's pretty simple. So for our example, if we have our 75% efficient machine, said if it requires 10 joules of work input to operate, then the work output is going to be 75% of 10 joules. So we can just solve right here. So it's this equation right here is just a different variation of that right there, and we can figure out that our work output is 77.5 joules. And we have some better examples in class that we will go over that make this a little more easy to understand as well. So just know that efficiency, for now, the percentage of the work input that becomes work output, and Again, there's a lot of different ways to try to increase efficiency. One is by reducing friction. And then there's roller bearings that reduce the friction of rotating wheels. And again, we talked about rolling friction is less than sliding friction, so that's why they use those. And to further reduce the rolling friction, the roller bearings are also lubricated with grease. So there's a lot of different things, again, to try to overcome friction to make efficiency greater. And then there's actually people do a lot of experiments. These engineers are using the flow pattern of the smoke trail. So you can see right here this trail of smoke going over top of the car to determine the fluid friction forces, the air resistance acting on the vehicle. And then they use the data to optimize the vehicle's shape for maximum fuel efficiency. So this is some real-life application stuff going on here. Again, they are actually using the things we are learning about to increase efficiency in cars as well. So I know it's a little bit longer, but that's okay. So let me know if you have any questions.